Hi, I'm Pamela Douglas. I'm delighted to give the next lecture in this educational session at Ohbm. Now that we know the basics, let's start going deep. If you're listening to this lecture, then you've probably heard of deep learning. In recent years, deep learning neural networks have transformed computational analysis across a variety of domains. The deep learning approach to reinforcement learning quickly learns video games. Algorithms for self-driving cars have rapidly improved, and generative adversarial models can create 3D reconstructions of faces from 2D images. Deep learning has also been used to make new discoveries in neuroradiology. For example, conventional wisdom for radiologists was that there was no information inside a tumor, and therefore one should examine only its borders. However, a recent deep learning approach, coupled to texture analysis, found prognostic information within the tumor itself. So the goal of the next 20 minutes or so is to provide you with a primer on deep learning neural network models and an intuition about how they can be useful in the context of cognitive neuroscience and neuroimaging. First, we begin with artificial neural networks, which are a class of statistical models that are loosely inspired by biological neural nets. They date back to at least 1943 with early work by McCulloch and Pitts suggesting binary units that summated continuous inputs and eventually implemented linear thresholds for categorization. In some sense, this was an early attempt to bridge spiking neurons with categorization, which is, of course, a hallmark of cognition. Discriminating categories that are not linearly separable in the input requires an intervening or hidden layer of nonlinear transformations between the input and the output units. The basic unit of an artificial neural network first uses its weights to compute a weighted sum of its inputs with a possible bias term, and then passes this result through a static nonlinearity called an activation function. Lastly, the output provides some additional transformation after the nonlinearity to complete the task the network is asked to perform, thus producing the unit's overall activation or decision. The goal of the model is to approximate a nonlinear function that maps input variables to outputs by adjusting the weight parameters. Feed-forward models, sometimes referred to as multi-layer perceptrons, are the foundation of many neural network models. They implement a chain of functions mapping input to output through the hidden layers. The length of the chain determines the depth of the model, and the dimensionality of the hidden layers determines its width. Feed-forward networks are classically represented by acyclic graphs, where input, hidden, and output variables are nodes, and the weight parameters are directed edges in the graph. The activation functions are typically not shown explicitly on the computational graph. At each layer, the data undergoes an affine transformation followed by a nonlinearity, thus producing a new representation of the data. Fascinatingly, a feed-forward network with at least one hidden layer between the inputs and the outputs are universal function approximators, meaning that if we add enough hidden units, they can approximate any mapping from input to output. So to gain intuition on this, I like to think of signal processing. If we had an infinite number of scaled and shifted exponentials, we could eventually describe or approximate any signal. Here we have weighted inputs that have undergone a nonlinear transformation by an activation function like a sigmoid. With an infinite number of these summed together, we could approximate any function that maps input to output, at least in theory. Of course, we are always limited by numerics and computation. So, if we can approximate any function with this simple feed-forward network, why would we bother going deeper? Well, deep learning models, of course, are hierarchical models that have more than one hidden layer. In contrast to manually engineered features, deep learning algorithms learn the features or representations through the data transformations across the layers. They can be very useful if the task requires multiple steps, or if a representation is composed of more simple elements, such as naturalistic images. Empirically, depth results in better generalization. And interestingly, shallow networks can require not only more parameters, but sometimes exponentially more parameters. In this sense, the deeper model is more compact and parsimonious. Given the computational burden of these models, sparse models may be advantageous when considering numerical overflow and underflow. If you're interested in numerics, you might check out Greg Chiar's Ohbm poster this year, which has a fascinating study on Monte Carlo arithmetic. So, what are the ingredients that we need for deep learning? We need to, of course, define our model architecture, a cost function, our optimization procedure, and our training data. As you learned about in previous lectures, there are semi-supervised learning schemes and unsupervised learning without labels. In this lecture, we'll mostly consider the classic supervised case, where the training data have labels. So first, model architecture. There's a huge taxonomy of models, from simple perceptrons to winner-take-all to different levels of biological inspiration in the model design. So with this huge taxonomy, how do we choose? As we've just seen, networks that are too shallow may overfit. However, excessive depth can sometimes lead to vanishing gradients. Are there guiding principles to help a user define the number of layers, the dimensionality, and the model connectivity? Unfortunately, the short answer is no. The no free lunch theorem demonstrates that no one algorithm is universally optimal. Averaged across all possible data generating distributions, algorithms will have the same error rate on unseen data. As neuroimagers, we may wish to use biology to constrain the topology of our networks, particularly if the goal is to use deep learning as a model for brain information processing. For example, if you're studying vision, you may wish to constrain the deep learning model layers to match the hierarchy of processing in the human visual system, enabling the testing and examination of other aspects of the model. In previous lectures in this session, we learned about objective functions. In the case of a linear model, a measurement like mean squared error may be used to quantify the model's goodness of fit to the data. In this case, the goal is to minimize the mean squared error by adjusting the model parameters. When the goal is to minimize the objective function, it is often referred to as a cost function or a loss function. But how do we define the cost function for a deep learning model? There are many statistical approaches to define objective functions. Some machine learning algorithms, like decision trees, for example, can require bespoke considerations when defining their objective functions. Thankfully, in deep learning, it is common practice to use the maximum likelihood principle as a guide for defining our cost function. The maximum likelihood principle is a common framework used in deep learning for density estimation. It provides a framework for estimating model parameters, where iteratively adjusting the weights can be cast as an optimization problem. It can be thought of as an attempt to make the model's distribution best match the empirical distribution from the training data. The principle of maximum likelihood, originally developed by Fisher in the 1920s, states that the desired probability distribution is the one that makes the observed data most likely. Therefore, we seek the weight vector that maximizes the likelihood function. Equivalently, we can frame this as a minimizing problem where we minimize the dissimilarity between the model and the empirical distributions using the KL divergence. With terms dropping, we are left with minimizing the cross entropy between the two distributions. Note that the specific form of the cost function does change from model to model, depending on the specific form of log P model. Now that we have our objective function, how do we adjust the parameters to improve or minimize our cost function? Because loss surfaces can be complicated, as shown here from work in Tom Goldstein's lab. Because the goal is to minimize a function, it may be useful to recall concepts from basic calculus. If one takes the derivative of a function, this provides the slope. At the extrema of a function, max or min, the slope or the derivative vanishes. Therefore, to find an extrema, one may wish to take the derivative and set it equal to 0. The derivative also tells us which direction to move in order to minimize the function. We should move in small baby steps in the opposite direction of the derivative in order to minimize it. With neural network models, we have multiple inputs. Therefore, we must compute the weight vector of partial derivatives, or the gradient. The gradient reflects how much the error changes with an adjustment of a weight. The learning rate here controls how big or small the baby steps are that we adjust the parameters in response to the gradient. But how do we actually compute the gradient from a deep learning model? That's where backpropagation comes in. Backpropagation is essentially a clever algorithm that allows us to calculate the gradient in an efficient manner by reducing repeated computations and propagate the error backward through the network, hence the name backpropagation, using the chain rule of calculus. Backprop is also credited with inspiring the second wave of neural networks in the 1980s. So just to summarize, backpropagation computes the gradient, but gradient descent or stochastic gradient descent is the learning algorithm that performs the learning by iteratively adjusting the parameters based on the gradient. So now that we have our model, our objective function, and our optimization procedure, we still need to specify the form of the nonlinear activation functions. There are many. A few are shown here. Some are thought to resemble the rectified linearity found in voltage-gated ion channels. In deep learning, the rectified linear or ReLU function has become the activation function of choice. It simplifies the gradient descent learning of the weights, enabling more rapid training, and works very well in computer vision and other domains. Also, the fact that the gradient is 0 in half of the function means that some of the units, or neurons, are not on, thus simplifying the calculations. The last ingredient is data. The more data, the better. Increasing the size of the training data improves generalization until either a minimal error is achieved or until an asymptote has been reached, depending upon your model's representational capacity. One can improve generalization by adding extra copies of your data that have been modified with small perturbations. Some examples include small translations, rotations, or changes in color. Another augmentation that can be made is adding noise. Adding noise can also be beneficial for data augmentation and regularization. Even small amounts of teacher noise can actually boost performance. However, in the neuroimaging world, we should probably avoid right-left flips because it can, of course, create confusion with radiological convention. Lastly, regularization can be particularly helpful when training sets are small, which is generally the case in neuroimaging considering the high dimensionality of the data. Classic techniques such as weight decay that you learned about earlier in this session also work well in the deep learning session. So in this case, a penalty term is added to the cost function. This can result in the model putting weight on fewer of the features, depending on the selected penalty term. Deep learning also has its own methods for regularization. Numerous methods involve stochasticity and sparsity. But just as there is no free lunch for architecture design, there is also no free lunch for regularization. But what about convolutional neural nets? Convolutional neural nets are simply neural networks that replace the classic matrix multiplication with convolution in at least one layer. Classically, the kernel we convolve with is much smaller than the input dimension, resulting in a more parsimonious set of weights in subsequent layers. If the parameters are shared, this creates an equivariance to input translations. Convolutional layers are typically followed by an activation function and then a max pooling operation, which helps make the representation invariant to small translations or rotations. Pooling over separately parameterized convolutions helps the model learn which translations it should become invariant to. Other techniques, such as striding the convolution or skipping some positions, also promote sparsity. Also, interestingly, like biology, convolutional neural nets have receptive fields. The units in the deeper layers of the CNNs have larger receptive fields. Similarly, higher levels of processing in the brain also have larger receptive fields and tend to have more drift in terms of the representations. Up until this point, we've been mostly talking about feed-forward neural networks, but the architecture of the cortex includes top-down, bottom-up, and recurrent connections. Whereas feed-forward neural nets are universal function approximators, recurrent neural nets are universal approximators of dynamical systems. So depending upon the application, you may choose to use a feed-forward or a recurrent neural network. But how are deep learning models useful for neuroimagers? Deep learning is something that has been applied for many, many years for group membership classification of structural MRI. Oftentimes, in neuroimaging and medical applications, the goal is to utilize deep learning for the dual purpose of prediction and interpretation. And saliency methods aim to rank the explanatory power of input features or voxels in the image. A number of saliency methods exist that take somewhat divergent approaches. Many of these methods require hyperparameter tuning or identifying the appropriate reference in order to be robust to adversarial or even didactic perturbations. Recently, inspired by work from Goodfellow and also Talia Coney's Ohbm lectures, my group decided to introduce a panda to our images to provide somewhat of a ground truth for these saliency and relevance mappings. Unfortunately, many of the methods we tested were not robust against adversarial noise in the wild or noise common to the MRI setting, such as Rician noise. And unfortunately, the panda was missed, particularly when it provided redundant information. So if it was in the top left corner, the subject was typically developing, or the top right corner, the subject had ADHD. And so the model tended to favor one or the other corner in terms of assigning relevance. This is, of course, a similar effect that occurs when one applies L1 regularization to linear models. A second way that deep learning can be very useful in neuroimaging data is if you're using deep learning as a task-performing model of brain information processing, one that bridges Mars levels. Deep learning models provide some of the best current models for internal representations across levels of hierarchical processing in the brain. However, multiple deep learning architectures can learn simple Gabor-like features in their early layers. Therefore, testing a single deep learning architecture and finding V1-like representations should not be interpreted as evidence in favor of that particular model. A good fit, or a biologically plausible feature map, may be considered necessary, but not a sufficient condition in favor of a particular model. So, in order to avoid the single model fallacy, one should test multiple model architectures as candidate hypotheses. The central question then becomes, how do we select the best model amongst competing models? A short answer is that a model should be selected based on its generalizability and interpreted in the context of what level of generalization that the model achieves. So just to conclude, like brains, deep neural networks have feed-forward and recurrent connections and have receptive fields, and also many parameters, which is to be expected of intelligent systems. Deep learning can be used for representational models, such as encoding or decoding, and it can be used for group membership prediction. Great care should, of course, be used when interpreting these models in terms of their saliency methods and making sure that they're, in fact, robust to different perturbations. To avoid the single model fallacy, multiple models should be tested and they should be evaluated in terms of the level of generalization they achieve. For example, on the same data held out, on new measurements, the same individual, new individuals, or to new stimuli and tasks. So, an excellent resource if you're new to deep learning or even have been a practitioner for many years is the Deep Learning book, which is, of course, freely available online. Above, there's also 4 other books that I like quite a bit. This Explainable AI book is nice if you're interested in transparency methods for deep learning. And again, if you're interested in deep learning, you might check out the full course, the full educational course, which has been running for 3 years now at Ohbm. I helped organize the first year, and now the organizers have continued on and continued to update the deep learning course with notebooks, videos, and slides. There's also some nice links here to different videos and tutorials. And also this paper, this 2015 paper by Nico Krieges-Korte, is a really nice primer on deep learning for neuroscience. Thank you so much, and I look forward to questions and comments.